Okay, hello and welcome to the INQA seminar for today, the 20th of May, 2025. And it gives me great pleasure to introduce today's speaker, who is Reece Robertson. So Reece is a PhD student at University of Maryland, Baltimore County. And Reece will be talking to us today about Simon's period finding on a quantum annealer. So over to you, Reece.
Yes, thank you. Thank you for having me. So again, my name is Reece Robertson. I'm a PhD student working with Dr. Sebastian Defner at University of Maryland, Baltimore County. Be talking about Simon's algorithm on the quantum annealer, which is a study I just did with collaborators, including Zachariah, who's on the call, my advisor, and others. And let's get into it. So I'll start with a bit of background material. First on, I'll start with the key points. So the things I want you to take away from this talk are the following. First is that we've introduced a new adiabatic algorithm, which can be used to solve Simon's problem and more generally any problems which involve function inversion. Our algorithm showed exponential asymptotic scaling on noisy hardware, and a classical algorithm that solved the same problem had quadratic scaling. So there is that difference in performance from the quantum to the classical. However, our algorithm does avoid the problem of solving a noisy system of Boolean equations, which is required for the gate-based equivalent of Simon's algorithm. So there is a large savings in post-processing complexity that comes from this adiabatic implementation. Now we'll get into background material. Okay. There we go. So the first thing I'll talk about are the different computational paradigms, which is probably familiar to those on the call or watching the video. So I'll go through this quickly. There are two leading quantum computational paradigms right now. Arguably, there are others, but two that there's a lot of actual hardware for. The first is the gate-based quantum circuit model, and the second is adiabatic quantum computation. So for gate-based quantum computing, we have some quantum state we would like to prepare. Here I've denoted it by psi final. We are given a set of qubits in some initial state, psi initial, and we would like to perform an algorithm which is given by some unitary u. And in the gate-based quantum computer, we decompose our large unitary u into a sequence of smaller unitaries that act on 1 or 2 qubits at a time. And the product of this sequence is equal to the action of the full unitary. And so we do our algorithm by doing a sequence of operations on our initial state to evolve it to a final state using discrete operations at discrete time steps. So some companies in the industry include IBM and INQ and others. There's a lot more big names and startups, the whole board. So IBM does superconducting hardware. They use transmons in pairwise connected layouts. You see a schematic for an accessible IBM device. This is on the cloud. The other approach is the trapped ion approach, championed by IonQ. They use ytterbium atoms in a fully connected chain of ions. Here's a schematic for one of their computers. So these are fully connected, but they are more limited in scale. And then there are other quantum systems, virtually any two-level quantum system, or a quantum system in which you can isolate two levels can be used as a gate-based quantum computer. The other paradigm I'll talk about is the adiabatic quantum computation paradigm, which uses Hamiltonian evolution. So rather than doing a sequence of discrete gate operations, we will start with a set of qubits, which we prepare in the ground state of some Hamiltonian that is easy to prepare. We then encode our problem into a problem Hamiltonian. So the ground state of the problem Hamiltonian represents the solution to a problem we'd like to solve. And then we adiabatically evolve from the starting Hamiltonian to the problem Hamiltonian. If we do it sufficiently slowly, or we utilize an appropriate shortcut, then when we measure our qubits at the end, there's a high probability they will be in the ground state of the problem Hamiltonian, and they will represent a solution to the problem. So the champions of quantum annealing or adiabatic quantum computation right now is D-Wave. D-Wave builds quantum annealers out of superconducting systems. Quantum annealing is a subset of adiabatic quantum computation. So they use Ising Hamiltonians. So it's not general universal adiabatic quantum computation, but they can do anything you can do with an Ising Hamiltonian. And here's some schematics of the different, or some images of some of the different chips. This is an IBM chip. And of course, within this chip, there's superconducting circuits that are physically attached to a circuit board. This is a picture of an IonQ chip with an artistic rendering of ions superimposed here. So within these chains, or these traps, we have these chains of ions. And then this is a D-Wave chip with the superconducting qubits within there as well. Okay, so with that background, now we'll get into QUBOs. QUBOs are quadratic unconstrained binary optimization problems. So I mentioned a moment ago that D-Wave machines use Ising Hamiltonians. Ising Hamiltonians can be equivalently expressed as QUBOs. So a QUBO is a problem of the following form. We need to minimize X transpose QX, where Q is some symmetric n by n coefficient matrix, and then X is a binary vector. And so we have a problem, we have a number of variables that can be on or off, and we have to figure out the optimal assignment to minimize the total cost of this exponentiation, or of this multiplication here. Now, the last bit of background I'll talk about is Simon's problem. So Simon's problem is the following. We're given an oracle. So Simon's problem takes as input some oracle function, which for Simon's algorithm, this function is a 2-to-1 periodic black box function. So I have a function f, which takes bit strings of size n into bit strings of size n minus 1. And it's 2-to-1, so every output is reached by exactly 2 inputs. And then we're guaranteed that there exists some non-trivial s that's hidden within f, such that if f of x equals f of x prime for x not equal to x prime, then x equals x prime plus s, where this O plus is denoting the bitwise exclusive OR. So equivalently, x XOR x prime is equal to s for all pairs of x and x prime. And so s is the secret string or the period of the function. Our goal in the algorithm or in the problem is to find s, to find the period. And the only allowable operation we have is the ability to query this black box oracle f. So how do we solve this problem? Simon introduced the problem in, I think, 1994, and then the paper was published in 1997. The classical solution is to query f repeatedly until we get lucky and find 2 inputs that give the same output. So in general, classically, one query of f gives us no direct information about the period. Querying the oracle doesn't tell us anything about its period. It just gives us an input-output evaluation for a chosen input. And so we have to repeat queries until we find 2 that match, and then we XOR the 2 inputs that gave the same output, and that gives us the period S. The expected number of queries to find 2 matching inputs scales exponentially with problem size. Simon's algorithm is the gate-based quantum circuit solution to the problem. So in Simon's algorithm, we're given our oracle in the form of a unitary, so it can be operated as part of the quantum algorithm. So we're given some unitary U of f that acts on 2 quantum registers. It will take the first register, use that as input to the function f, and then XOR that with what's in the second register. So if, for example, this psi2 is the 0 state, then what the oracle for Simon's algorithm does is it takes psi1, will compute f of psi1, and store that in the second register. If this is 0, if psi2 is 0, then this reduces to just f of psi1. Simon's algorithm I've presented as a quantum circuit diagram here. Though the algorithm is successful because it uses this oracle to prepare a hidden subgroup. The hidden subgroup of interest I've called omega perp. So this omega perp is the set of all bit strings that are orthogonal to our secret string, right? So where omega dot s equals 0, where this dot operation is the sum of the bitwise product of the two vectors. And so we're able to, using this algorithm, we're able to efficiently sample from this set of bit strings that are orthogonal to our secret string. And once we've sampled n-1 independent bit strings that are all mutually orthogonal with the secret string, then we can compose a system of linear equations, solve the system, and deduce our secret string. And so in order to solve the algorithm using this method, we have to query our oracle on the order of n times to get our linear system. And then we have to do a classic linear solve to solve this system, which is at worst O(n) cubed, and likely you'd be able to do better than that. But in the worst case, you're looking at O(n) cubed, and so the entire runtime is polynomial time. And that's where we get this exponential advantage for the problem. So classically, we had an exponential number of queries. Here we have a polynomial number of queries of our oracle, and then a polynomial classical routine to post-process. Now, so far, all of this assumes that your qubits are perfect and that there's no noise. But we know that our quantum computers today are far from perfect. So when we have hardware error, then when we run Simon's algorithm and we get a sample, that sample could yield something that's not in omega perp. So we could sample something that is theoretically impossible given perfect qubits, but hardware noise could make these things possible. So we can have errors. And in general, without knowing how F is implemented, without knowing our oracle, we have no good way to differentiate between a valid execution of our algorithm and an invalid execution. So when we're sampling outputs, we can't tell if it's valid or invalid. So we conjecture that a vanishingly small amount of error may defeat Simon's algorithm. There's been a similar result, this paper here, where it was shown that a vanishingly small amount of error defeats Shor's algorithm, which Simon's algorithm is a foundation for Shor's algorithm. In addition, this figure comes from prior work I did with some of the same collaborators, where we looked at the effectiveness of Simon's algorithm on real hardware. So these figures, you're looking at problem size on the x-axis for 3 different IBM devices. And then on the y-axis, we have the percentage of invalid outputs, or the percentage of things that were not in omega perp. And you can see these blue lines are the real hardware. And by about problems involving 10 to 12 qubits, in all cases, our error states are occurring half the time. So at this point, the algorithm is effectively just sampling from the space of all possible inputs. We're not effectively preparing and sampling from a hidden subgroup. We're just sampling uniform, I imagine it's uniform random sampling across all outputs. But at any rate, the algorithm is failing here. It's not working at all. And so then if this happens, our problem becomes not a simple linear solve. Our post-processing problem requires solving a noisy system of equations, which has much greater complexity requirements, which, again, we conjecture will defeat the quantum speedup. This brings us to our adiabatic algorithm that solves this problem. So in the adiabatic algorithm, we're going to take the oracle not as a classical function, not as a quantum unitary, but as a QUBO, so that we can execute it on an annealer. here I've given an example of a QUBO. So let's suppose the secret string is the string of all ones. In this case, then our function f, to generate the output, it will take the XOR of each pair of inputs, and that will become the output string. So according to the D-Wave documentation, as per their documentation, you can encode the XOR in the following form. So we take x1 and x2 are the input bits, O is the output, A is the ancilla, and then computing this equation, it will be minimal when O is the XOR of x1 and x2. And then we can generalize this to n qubits. So if we replace our x1 and x2 with an x vector, our O and A with vectors themselves, then we can create this equation, which would be the oracle that we could put on an annealer. So this is our QUBO oracle that's given to us that we can use, and our goal will be to find the period that's hidden within this oracle. Now, of course, in general, we assume we don't know what this is, so this is just an example, but we assume that we're given an oracle, we're not quite sure how it works, but we do know where the input bits are, where the output bits are, where the ancilla bits are. So this brings me to the next point in our algorithm, which is the introduction of penalty parameters. So we're given an oracle, and we know where the output bits are. So what we're going to do is add penalty parameters onto the output bits. So I'm going to change my Q from equation 6 into this Q hat, where the only difference is I'm now conditioning on a penalty vector, and that penalty vector is utilized by just appending it to the penalty that's already on the output bits. So I'm going to take the oracle unchanged and just add on extra penalties onto the output bits. Now, why do I want to do this? I think it's best explained with a figure. So this is one example for a problem with an input register that's 3 qubits. So here I've evaluated the QUBO with no penalties. And I've done this analytically to get just the spectrum, the energy spectrum of the QUBO. So here you can see that without penalty parameters, we have a degenerate ground state that contains all valid function evaluations, all valid oracle evaluations. So our ground state contains every input-output pair that is a valid assignment from our oracle. If I were to run this on an annealer and sample from the ground state, I'm going to get one input-output pair, which is no better than what I would get classically. The only difference between this kind of sampling and classical sampling is that here I don't pick the input that I'm evaluating until after I've already evaluated the oracle, right? But other than that, I'm just going to run this. I'll get some input-output pair. I'll run it again. I'll probably get a different input-output pair with a different output. And I recovered no information about my period directly. But with penalties, we can change our energy spectrum, and we can isolate a single output in the ground state. Now, if I were to execute this and sample the ground state, the input value will be fixed. So that's the point of these parameters, is they're trying to fix a particular, and I said input, I meant output. It will fix a particular value of the output of the function in the ground state. And now the degeneracy includes only the two inputs that map to that output. And now if I sample this twice and I get each of the two inputs, I can add them together and solve the problem. If in general, if each input is equally likely to be observed, then sampling this twice, I have a 50% chance of solving the problem. If I sample it more times, my probability of success goes up. And with maybe 10 or 20 samples, I have a very high probability of success, given that both of the inputs are equally likely to be observed from this ground state. So that leads us to the next problem, which is on selecting penalties. So I'm going to say that let's fix f of z as the output register. And now there's z and z prime are the two inputs that are now in this degenerate ground state. I want the probability of z and z prime to be roughly equal. So we need to choose penalties that will do that appropriately. So first of all, the magnitude of the penalty, we found choosing a magnitude of 2 worked for all of the problem sizes we wanted. In general, it should be a positive, or the magnitude should be a low number. If it's too high, then the penalty constraints override the other QUBO constraints. And so then the minimal, all the values that are at the minimum of the energy spectrum have the same output, but they may violate the oracle conditions. So we don't want to totally wash out the oracle by setting the penalty too high, but at the same time, we need the penalty to be high enough that it's not ignored. We need to enforce the penalty. So we found that the magnitude of 2 worked well for the problems we were looking at. And then another thing we found is that the sign of the penalty mattered a lot. So assigning uniform penalties, if it was uniformly 2 for every output, that would heavily favor one z over another z. So we found for the secret string of all ones, alternating the sign balanced things out, or just randomly assigning a sign to each penalty balanced things out. And I'll note that these numbers in particular are given from one iteration with one single random assignment. So there are still random assignments that will favor one output over another, but repeating the algorithm with a new random assignment can address that problem, as there are assignments here that are much more balanced. So once you have your QUBO, you've added your penalties, then you're ready to run on real hardware. We tested this on the D-Wave Advantage 5.4 and the D-Wave Advantage 2 prototype 2.6. And we acknowledge Jülich Supercomputing Center for giving us access to these devices. And for fun, here's the embedding of a problem with a 50 qubit input register on the D-Wave Advantage 5.4 system. So that's what these are the qubits and connections that we utilized in that chip. And now we can get to the results. So this figure, what I'm showing you is the successes per shot percentage, or essentially the number of shots that succeeded out of 4,000 total shots. So I'm fixing the number of shots I executed at 4,000. I fixed the annealing time at 100 microseconds. And then as a function of problem size, we'll look at our success percentage. And we see that on both devices, our success rate goes down as the problem size gets bigger. And here, I guess a successful run is one where I successfully sample from the ground state. And so I'm getting one of the inputs with the output that I've tried to isolate in the ground state. So in the short term, the success rate decays as the Gaussian, and in the long term, it decays exponentially. So we see our success does go down as problem size goes up. So in the presence of noise, it becomes more difficult to sample from the ground state directly. I want to show this figure as well, which is the runtime. So in this figure, now I'm going to fix the number of successful samples at 2, and I'm going to look at how many expected shots must I evaluate for each problem size to find 2 successes. And again, our annealing time is fixed at 100 microseconds. So the runtime is entirely a function of the number of shots required. And again, we have an exponential increase in runtime as a function of problem size. One exciting thing here is that the newer generation of D-Wave machines has a lower coefficient on the exponential. So it outperforms the first generation. And it remains to be seen if future generations of the D-Wave device will be able to change the character of this curve away from the exponential. But we do see improvement between the generations. The other thing we did here was test this against a tree search algorithm that D-Wave implements. And the tree search algorithm showed quadratic asymptotic scaling, which intuitively I think makes sense, because when we can represent our problem as a tree, every new qubit is adding a new layer to the tree. So even though the size of the tree grows exponentially, a heuristic search algorithm really just has to search one more layer of the tree to look for the minimal solution. So we can avoid that exponential scaling. So this brings us back to the concluding remarks. What we've done is introduce a new adiabatic problem or algorithm to solve Simon's problem. And in general, our algorithm is a function inversion problem. And so it can be used to solve any sort of function inversion problems. I've linked one paper here where the researchers used the gate-based Simon's algorithm to solve abelian hidden subgroup problems. And so ours could be used similarly. Our algorithm exhibited exponential asymptotic scaling under noise. While I'm here, I'll point out that the number of successful samples from the ground state in our algorithm remains fixed at 2 or 10 or 20, whatever you would like to have, whatever threshold confidence success for solving the problem. So to have a 50% chance of success, 2 samples are required from the ground state, and that is constant independent of problem size. The problem of actually sampling the ground state twice, that's where the exponential runtime comes from. So if we were able to sample from the ground state every time, then the algorithm would be constant time. But as it stands, we can't do that. So we have exponential asymptotics in our noisy environment. The classical algorithm we looked at scales quadratically, but our adiabatic implementation that solves Simon's problem avoids this problem of solving a noisy system of equations, which is required on the gate-based systems. In closing, here is a link to the paper, and I've also included a link to my website, which has a link to the paper as well, which I would invite you to peruse at your leisure. And I want to thank you for your attention.
Great, thank you very much, Reece. Very interesting presentation. Round of applause from me on behalf of all the attendees.
Thank you.
And I guess I'll open this up for questions. If anyone has a question for Reece, either turn your camera on or raise your hand, as Dennis has just done. So Dennis, you have a question for Reece?
Yes.
Yes, yeah, thank you very much too, actually. So yeah, thanks for the talk. My first question is about the success probability, where you showed a Gaussian fit and an exponential fit into different regimes. And
Yes.
from just naively looking at the points, I'd say that both a Gaussian and an exponential with the right parameters could fit these data points. Do you have any other argument why you take the Gaussian and the exponential in these two problem size regimes?
So yes, I agree that Gaussian and exponential probably could both be used to fit. It was just looking at the best fit. A convolution of the two seemed to do the best. We wanted to acknowledge that in the near term, Gaussian fit a lot better, but in the long term, it started to move away. So the best fit we found was to take the convolution of both. I'd have to think a little bit more about other arguments as to why we would do that. But does that answer your question?
Yeah, and to some extent, yes. I mean, it's not unusual that people take for smaller problem sizes the Gaussian and for the long tail the exponential. I just wanted to see what if you have any particular argument for this. But no, but that's fair. I can go with that. My second question is this tree search algorithm that D-Wave implemented. Is that one of the open source packages that D-Wave publishes, or what's behind that?
That is a good question. I'm not sure if it's open source, but it is in their documentation. I'd have to look at that, and maybe I can send a follow-up. I hesitate to say it's open source, but I would be kind of surprised if it wasn't.
Mm.
But yeah, I'm not sure if they would have anything proprietary.
But it's not like one of these standard packages that they like. Does it have a name actually? This tree solver?
I don't believe it has a unique name. We did look at in the paper. We did look at another package called VLOX-Q, which this one is a lot, it is named, it's a QUBO solver that's optimized for these kind of QUBO solvings. And that outperformed both of the devices as well across all times. And on the interval we tested, it ran in nearly constant time. So there are classical optimized algorithms that are not open source that can do very well with these problems.
Okay, yeah, thank you very much.
Yes, yes.
Any other questions for Reece from any member of the audience? Either turn your camera on or speak up or raise your hand or post something in the chat if you wish. Well, I have a question which maybe reflects a lack of understanding on my part, but could you go to page 16 of your slide presentation, please?
Well, of course, yes.
Which was some timing metric, approx runtime. Yeah, okay.
Yes.
So I guess there's a couple parts to my question. Do you know the correct solution a priori here?
So in these problems, we've taken S to be the string of all ones, and so yes, we do know what it ought to be. And this is representative of one of the simplest cases for annealing, because the string of all ones gives a QUBO that has this very regular structure where it's the XOR of all inputs.
But in general, if you're doing it with an unknown string S, is there a quick check like there is with factorization, or is there no quick check once the solution is returned?
So when you've found in our version, what you would do is you would find two inputs that you would add together and would be a candidate secret string. The quick way to verify that is to evaluate the oracle on that candidate string and then evaluate it on 0, and those ought to be the same. Because 0 plus S equals S. And so, and when I say plus, I mean the bitwise XOR.
Yeah.
So therefore, F of 0 and F of S should be equal. So that's the way to verify, is to check, does it satisfy?
So earlier on, you were saying that when you were running this algorithm on gate-based approaches, you got a correct probability of a half or something. So to me, that suggests you just need to run it 2 or 3 times and check it every time, and then you'll find the correct solution.
Yes.
Have I got that correct?
Exactly. That's exactly it. Yeah. So when I said the half, that's, let's say I sample from the ground state twice. And so then I'm getting, with probability a half, I would get both Z and Z prime. So I would get 2 unique inputs that go to the same output. And then I add those and I get the solution. I think maybe there is a problem where you have a candidate solution and you want to verify if that's accurate. So I could have 2 samples that I think came from the ground state, but actually didn't come from the ground state. And then I would get this candidate solution that I would believe was S, but then I could easily check that and find, oh, this is not S. In which case, then you rerun the algorithm and your probabilities are the same from run to run. So you're back to
again, just to make sure I've understood, you only need to run that of order 1/2 times approximately.
Yeah.
Okay.
Yeah. So and for the gate-based algorithm in particular, I've linked a textbook here. So Merman's book in which I can follow the link. In this book, he has an appendix where he outlines the probability of success in Simon's gate-based Simon's algorithm, and makes the argument that evaluating your oracle n plus 20 times in a noiseless setting gives you 1/1,000,000 chance of failure. So you can do with this constant small increase over the required number of samples, you can get arbitrary accuracy. And so then that fixes the number of oracle evaluations as a linear number of evaluations for the gateless system.
Okay.
For our system, you need the constant number of valid ground state samples, but then there's the exponential number of samples that are required to get the constant number of ground state samples.
Okay, cool. I'm understanding it more. Thank you very much.
Yeah, those are good questions.
Any final questions for Reece? If not, let's thank Reece again with a round of applause on behalf of everyone here. And we'll round off just by saying I look forward to seeing you at next week's seminar, which I don't have the details of in front of me, which is bad. But no matter. I'll look forward to seeing you all there in a week's time.
Yes, thank you for having me.
Bye-bye, everyone.